Oh, sorry.
but also
Thank you.
experts and also kind of the person that's
Is it good?
So I did want to remind you all of the embargo. The embargo, the information that we're sharing with you will be embargoed until 8 a.m. March 7th. So please keep it the second time. Please keep that in mind when we're putting that embargo time is coincident with the Open Compute Summit, where we'll have more information that we can talk about our receiving. So the news that we are sharing with you is really the next set of architectural detail around the Naples platform. So as you heard from Forrest in the keynote session, we're now starting to get very specific information about the Naples device itself in anticipation of its launch later in the second quarter of this year. So important to note that we talked about the fact that we have a very strong addition in core count and core density through having 32 cores, 64 threads per socket, which means that in a two-socket system we have a full 64 cores and 128 threads. The other architectural detail that we're revealing is the addition on each individual Naples product of 8 memory controllers per CPU. And the reason we do this is we want to make sure that we feed these high-performance cores with industry-leading memory bandwidth and capacity. Okay? The other major revolution that we have here is the fact that this is a fully integrated SoC. So this means that we've done away and eliminated the need for a separate I/O bridge or I/O hub or south bridge, and all of the I/O is now fully integrated in the die. It gives us the capability to have much higher density, much lower latency for attachment of many different types of peripherals. So when you think about how this works, we also include the Infinity Fabric, which is our coherent interconnect between the two CPU complexes. Right? So as I talked about, in addition to kind of the core density, we talked about the fact that we're bringing back SMT, so simultaneous multi-threading. That means we have the ability to run either single-threaded or multi-threaded in the application. And all of these things really kind of translate to a fairly substantial level of system level value. So, excuse me, when we think about our re-entry into the data center market, we're also putting a lot of effort to ensure that it is easy to adopt our technology. The current x86 server users will be able to quickly adopt what we're doing with Naples. So this includes, beyond the core itself, beyond the device itself, the entire tool chain that leverages the ISA-specific nature of x86 to include things like compilers and libraries that allow you to leverage what you do today on x86 quite easily. We also have support for all the standard interfaces for things that you typically get accustomed to in the server world, like UEFI-based routing strategies or BIOS, as well as IPMI for system management. We are also working directly with all of the major OS and hypervisor vendors to ensure that whenever we have Naples in production, all of the major OSs and hypervisors will be supported, such that the native application platforms can be run on top of those OS and hypervisors safely. Finally, we are focusing at the application level. So when you think about the types of features that we have in Naples, leading core density, leading memory bandwidth, leading I/O, things like data analytics, when we're dealing with large sets of data, the ability of our solution to actually leverage all that memory bandwidth capacity means that we have a measurable benefit as it relates to performance in database applications. When you look at the I/O that we have, the ability to actually now connect a very large number of storage peripherals. So things like NVMe or SATA-based devices that means it's essentially greater storage by having a lot of capacity directly connected, not through a PLX switch or an I/O hub, and then improves latency because of that direct connection. And finally, when you look at our core density and very strong balance of memory bandwidth, for things like virtualization, the cloud, right? When people are very focused on getting the most VM density out of their solution, we think Naples will do very well. It's all about doing this in a very bespoke power envelope. So a lot of the technologies that you saw, both from a power and performance perspective, that you saw with SenseMI and that kind of Sam talked about on the panel, those are all the same techniques that are employed in Naples. Okay? So with that, I'll maybe turn it over to Dan to talk a little bit about the demo.
So what we wanted to do is give you the opportunity to see the demo a little bit closer. We know it's difficult to see how well the demo plays and the performance that it displays in a keynote environment. Obviously, it's a little bit loud, so we apologize for that. But what's really critical is we wanted to show something more than just a synthetic workload in this time frame. We also wanted to show something that highlighted the architecture that Scott just showed. So one of the things that we thought we'd do is take a particular workload that tends to be a little more gated in terms of memory bandwidth. And in this case, we're taking a seismic workload. And this is a set of algorithms that could very well be used for a lot of different analysis of heat transfer and fluid dynamics. But in this case, we're taking a fairly, it's a computationally complex problem iterated over 10 iterations. And what this allows us to do is to start to stress the memory bandwidth of the system, in some ways the memory capacity of the system, and also there are balance points between the core infrastructure, the memory topography, and as well as the speed or frequency of the memory. So the intent is to draw for each one of those. So in the first workload that we're going to run here, the first trial, what we wanted to do was give you an apples-to-apples comparison, so an equivalency comparison. Today, if you take a look at what Intel offers the market, at the very high end of its E5 stack is the 2699A V4. So this is a very expensive part. This is the highest end of their E5 product line, a $5,000 part. We took that same part and we set that against the upcoming Naples processor. What we disclosed to you in this time frame is this is 64 cores of compute capability, but in this case, we're limiting that down to 44 cores. Equally important is in this first set, when we load up a full memory capacity with the Intel box, it's clocked down to 1866. So again, to make it as equivalent as possible, we clocked our memory down to 866. And when we did that, what we saw is our performance was about 2x. We were about 2x faster in running through 10 iterations of this data set, which each iteration has about 1 billion cells that it needs to solve for. So not an inconsequential workload, and more importantly, we're doing it in twice as fast as what the competition is. And that's before we actually go to step 2. And step 2 was all about making, unleashing the capability of Naples. So in this step, what we did is we kept the samples of the problem size the same. So again, 1 billion cells over 10 iterations. But this time, we've got memory clocked up to entitlement. We've also got all the cores. So now we've gone from 44 cores to 64 cores. Another note here is it's pound for pound. So we've got hyper-transport enabled, and we have the simultaneous multi-threading enabled on the Naples system. And so as we go through this, what you see is, again, Naples comes out very quickly. There's a piece that we did not show you that you're actually seeing now, which is in order to get to the runtime component of this demo, there's a memory load capability as well, right? So the problem set is spread out and is addressed to the memory that you've got in system. In this case, that actually adds time. So when you run them side by side and you run the full gamut of loading to memory and then runtime, what you see is this delta is just exacerbated. So 2.5x faster when we unleash the architecture of Naples. And then finally, what we said is, what happens when we get a little bit closer to what a real-world workload would look like? And in this case, we took that billion cell problem set and we quadrupled it. So now for each iteration, we're going to run computations on 4 billion cells. When we do that, there's a couple of points. One, Joshua kicked this off a while back, and what you find out is, as we're in runtime, Intel is still trying to load the data, and in fact, fails to load. So this is a size of problem set that Intel can't actually load to memory. We did our best to normalize everything. So we took 16 gig DIMMs, kind of the industry standard at this point, loaded it up, and what you find is memory capacity also matters when you're looking at workloads like this. So we want to get as much of a problem set as close close to the CPU as possible, with the highest bandwidth as possible. And that's essentially the payoff of the Naples architecture. If you compare us to what's currently available in the market, this is the key point. When you look at where Broadwell is today, and we can't speculate on where the competition is going to be, but we have a good idea. Perhaps these numbers aren't quite as good, but they're still extremely compelling. We believe this is quintessentially what sets Naples apart in this time frame. 122% more memory bandwidth. That matters. Memory is one of the biggest issues especially in the two-socket space today. We're addressing that. 60% more I/O. So when we talk about attaching accelerators and non-volatile drives, high-performance drives, this is absolutely critical. And finally, it's about balance. So we talked about 64 physical cores and 128 threads. This is a radically new set of resources and capabilities that we think customers are going to be delighted to kick the tires and deploy in their data centers. So with that, I'll pause. That's sort of the prepared material. If you guys have questions, we'd love to answer. And you're going to have to, it's hard to
pick up on it, please.
So I would say, we'll optimize until we absolutely can. So what you're seeing now is not a production platform, but we're getting really close. So we're committed to launching this in the first half of this year, which means the clock is ticking. But we'll make every effort to make it.
So it is 2.5x plus.
Sure. Now remember, the 2.5x, this is really a commentary on the system performance. There's lots of ways to cut performance. And so we look forward to the opportunity to come back and talk to you again when we start talking about per core performance. We start showing the implications of the I/O footprint for various benchmarks or workloads. This is sort of the first step in a journey towards Naples that we think is going to delight us.
Expecting from the
The other thing is that this 2.5x it's specific to this workload. So there are going to be other workloads that could be even higher, and some will be less. Okay.
other questions.
I'm Nico from EK Waterblocks. I would like to ask regarding the performance. Traditionally, the AMD Opteron, like the 6200, 6300, were really strong in the NC's CFX, which we are primarily using. But this was one of the software that scaled really well, like 16 cores for 16 threads. With the new design, let's say, with the Ryzen, we have SMT, right?
Yes.
Before we had CMD, now we have SMT. How is the performance increase compared to that? Do you have any?
On what workload were you mentioning?
CFX.
CFX?
Yeah.
From ANSYS?
Yes.
Okay.
So I think in general, you saw from Mark this kind of point of, from a bandwidth perspective and from a core scaling perspective, we see things being kind of very highly linear. And so we think that extrapolates in this level of scale as well. So if you looked on his chart, you saw that he talked about 8, he talked about 16, and then jumped up to 32 and 64. That's the data that's really based upon Naples. So we would expect that core performance would scale very well, and up even to those higher core counts.
Let me give you a little bit of a comment on this. So we're going to be testing some of those CFD applications. Okay, we've done in the past. We're going to be doing it. This specific one is also using MPI and OpenMP, like all of these codes. So this is a scaling. We're showing scaling up to 128 threads in here. So it's going to be similar behavior.
Very good. Thank you. Other questions?
One big configuration of the Naples has a 128 thread as a thread, and two big configurations each has a 64 and other AMD. So that it means that the AMD connect requires 64 bit thread in the drive.
Yeah, so you said it exactly right. So in the 2B configuration, we actually share the PCI Express physical lanes for the Infinity fabric. So this is the coherency connection. We can convert PCI Express planes to Infinity Fabric, and that's how we achieve coherent connection. We then take 64 out in the 2P system. So 128 total, 128 in between. So it's a very high bandwidth, very low latency connection. Other questions?
So just
Say again?
Can you show the actual frequency of running frequency for this
Running.
frequency?
Oh, we're looking at frequency. Now, at this point, we're not talking about specific power levels and frequencies, but expect that over the course of the time up to launch, we'll be sharing more information. Great. All right.
Yeah, so just a reminder to everybody, all the information that was disclosed in the Naples keynote as well as in the room today is embargoed until 8 a.m. on March 7th. That's 8 a.m. Eastern Standard Time. And if you have any incremental questions, Gary Silcott is the contact for our business. You can route questions through him and we'd be happy to answer them. Thank you all very much. Thank you. Hi.
Joshua, we got a quick question.
Go ahead.
Yeah. So can you tell us,